All right, so what I wanted to show next is an image from this book I'm working on.
How many books have you done?
I just published one this year. That was my first one. I've submitted some other chapters, but anyway, so this is more or less my little take or big picture on separating organic molecules from inorganic molecules. So, what's that? Yeah, exactly. So I sort of, I'm just calling this thing over here the biosphere, and really before humans showed up on planet Earth, there was only a biosphere. Well, there was nature, right? There's sort of portions of the Earth that are not alive, that don't include life. But once life shows up, there's a biosphere. Once humans come along, oh, and I like this. I've got the Garden of Eden in there. So once humans come along, start making rocks, melting metal, et cetera, et cetera. There's a little more tech. Humans come along and start making technologies. This whole technosphere sort of erupts or happens. You might argue that even early, bones and stoneworking was the technosphere, but relatively inert, right? So nothing that's toxic. So our challenge here as recycling technologists is to operate sort of in this realm. So taking things back from nature, and what I've done here, this figure was primarily for the purpose of water recovery. So let's say you've got your wastewater treatment plant, and the majority of that wastewater is just water. I mean, there's some solids in there, et cetera. But so you need to get that water off of there. My proposal was to take the water molecules themselves, and this would just be with electrolysis. And again, electrolysis is in the realm of the technosphere. It happens in batteries. We've got a 100 kilowatt electrolyzer sitting over at the Hive right now that we'd like to put back into use. But the idea is send the oxygen back to the biosphere, for goodness sakes. I'll tell you, and then send the hydrogen to the technosphere. So create the hydrogen economy, if you will, right? So you've got all this nasty water around, cook it off, boil it off, get the oxygen back in the air, because right now, if you look, and I have the data here right now. We hear a lot about the increase of CO2 in the atmosphere. We're also experiencing an oxygen deficit in the atmosphere. So, where does the CO2 come from? Well, it comes from carbon combusting with oxygen. Where does the oxygen come from? Well, it came from plants, but it's sitting there in the atmosphere for us to use. So let me just take a quick look. A colleague of mine sent me a paper. Here we go, right here, Polson. So these guys are measuring oxygen content in the atmosphere at the top of mountains in Hawaii, right? So, sure, they're kind of, close-ish to civilization, but far enough away that you would assume at some point it becomes fully mixed, right? So let's just take a look here. Chris Polson, and I believe my friend Steve Korick knows one of these guys. So right here, right off the bat, percentage of the Earth's atmosphere, and again, oxygen, one of those very important organic molecules that we're talking about today. Between 10 and 35%, they've been linked to evolution, radiation, sizes of animals, but not considered to affect climate. We considered simulations showing this modulation of the partial pressure of oxygen, namely how much pressure does oxygen add to atmospheric pressure, the rest of it mainly coming from nitrogen. Let's see what these guys have here. So this is mainly a simulation paper. Oh, and this is, yeah, sorry, I thought that was the, and I know I've got it here somewhere. Let's take a quick look for it. It's going to be in a PDF. It's the Mount Loa. Because what they're seeing, they're actually seeing the amount of oxygen in the atmosphere. Now I'll just have to Google it. Maybe I didn't save the paper. CO2 and REL supporting. There we go. Yeah, these are the guys. I think they actually have a data set. Okay, perfect. That's what I was looking for. So this is the O2 divided by the N2 ratio multiplied by 1 million. So we're basically we're starting out in 1990 through 06, and then each year just the amount of oxygen in the atmosphere is sort of marching down. What's even more notable to me is the curvature of this curve. So guys, just an informal what did you guys? Oh, what happened? Oh yeah, I think my oh there we go. Yeah, sorry. I think the PowerPoint screwed up the projection mode. So this is the oxygen nitrogen ratio multiplied by 1 million. So normally the ratio is, and this is the change of the ratio. The ratio in the atmosphere is 1 to 5. So 1 oxygen molecule per 5 nitrogens. And again, as I said, this is the Mauna Loa data. And so we're looking, so at 0.00248% is the drop. So basically going from negative 100, it looks like it's even a little more than that, almost 300 per meg is the direct result of global combustion. So someone might say, oh, how do you measure that? Well, you stick a probe up the top of Hawaii and see how much oxygen in the atmosphere. But here's the question, just informal poll of the class. Is this thing curving down or curving up? Or neither? It's going to do one of 3 things. So here's the question. So is the curve, let's do this. No, hang on. How do I do this? Yeah, there we go. Okay. So is that curve going like this, like that, or just flat? It looks to me like it's going to slide down. We could actually just take the thing. Let's just take a look.
Pretty close to it.
It's pretty close. Let's just copy the image. I'm going to hop into PowerPoint. I'm going to paste that here. Zoom it out a little bit. There actually are some pretty cool softwares out there for data reduction. So it'll go in, do an image scan of that, and then pop, and you can actually take it and sort of steal it, if you will, and pop it into Excel. But for our purposes, I just want to get a rough approximation of whether this thing is curving up or curving down. So I'm just going to put one little line there, one there, make it bigger. Format shape, solid line, I'll make it black, I'll make it a little bit thicker. I'll copy it, I'll paste it, and I'll just do the same thing down here. So those are both straight lines. And I have to say, if anything, there are more dots above the line than below. And all I've done is taken the lowest low point on the beginning and end, and sort of the highest high points on the beginning and end, and just roughly it looks like we're in this sort of downward spiral, if you will. And so yeah, I don't know. I guess where I'm going with that is, I don't know if you heard about the heat waves in India, for example, this past year. But one additional issue with climate change is that you've got heat waves somewhere. What happens? Well, you turn on the air conditioners. Well, where's the air conditioning come from? Well, it comes from burning coal. So you end up with this sort of perpetual nasty feedback cycle. What's that? $100 and then release more methane. Yeah, right, exactly. And so what we're trying to avoid is this sort of downward, and it's actually called a positive feedback cycle. It's not very positive. It's actually quite bad, detrimental for global civilization. But anyway, getting back to the lipids, this is also typically where these guys are going to end up when you talk about turning fatty solids into biofuels. And then finally, I just want to wrap up on my big picture. I just wanted to get back to this image. So really, our jobs as recycling technologists is to work in this sort of murky middle of separating biological organisms, molecules from technological molecules. Oh yeah, last thing I wanted to show on that is this whole phyto. Because, as we know, we can do our little sorting. We can stand at the recycling bin and put the glass over here, put the paper over there, put the leftover cheeseburger over there. Phytoremediation, though, is when the stuff's too nasty. So, for example, in my garage, I just have a bucket. It's a bucket of everything that's come off my garage floor for the last 2 years. And there's some plastics in there. There's some leaves in there. There's titanium shavings in there from when we were building a bicycle in my garage. There's, there's even some lead in there. The guy that lived there before left behind a couple lead bricks or ingots, and they're great doorstops, but where does that go? So I could put it in the landfill. I could dump it down the sewer. I could set it on fire, or I could come up with a cool phytoremediation strategy to let the smaller organisms do that work for me. So let's just take a look at phytoremediation. So rather than us, sorting through molecules with our hands, we're using typically plants, and it's not just like a plant goes and do this. It's all the individual little enzymes inside the plant. So mitigating pollutant concentrations. And a couple weeks ago, I showed you the research skills for going into ISI and digging through that. If you want to get deeper into that, I highly recommend going, because I know this is going to be a really big topic in sort of high-tech, nanotech recycling technology down the road. When all of a sudden, hey, sorry, you can't put your organics in the landfill anymore. Well, sorry, I'm pretty sure there's some junk in there. Well, it's got to be phytoremediated before it can go back into the agricultural system. So that's what this stuff's about. So again, polluted or suffering ongoing chronic pollution, and this is true. This is true on like our nation's interstates. I mean, just think of all the little chunks of rubber and metal and oil. It's there. I mean, where else is it going to be? It's all along our interstates. Here's one example: metal mine workings, polychlorinated. We talked a little bit last week or a couple weeks ago about dioxins. So there's your chlorine. Explosives. A lot of times explosives are going to have a benzene ring in there, that six carbon ring. Okay, so here are several plants that have been used: mustard seeds, alpine pennycress, hemp, pigweed, at hyperaccumulating. So these plants actually sort of take one for the team, if you will. They suck it out of the soil preferentially and more or less concentrated. So getting back to this slide, and there's always two separate theories on pollution control. One is just dilute the heck out of it, and the other one is concentrate the heck out of it. And really what these phytoremediators are doing is concentrating them. And in fact, that's exactly, Shelley, what you're doing in your electronic waste recovery. You're concentrating the gold, the heavy metals that otherwise would have just been diluted in the landfill. So, fundamentally, those are the two basic, right here, one of two things is going to happen. You're either going to concentrate it or you're going to dilute it. And the phytoremediators are concentrating it.
And once they concentrate it, can it be something where you can extract it and use it? Or is it not really enough?
Well, yeah. That's a great question. Let's just say, for example, one of these plants takes up lead in heavy amounts. Well, it's no longer sitting in the water where it previously was to get into the drinking water, groundwater. It's now in a plant. Well, I can imagine putting this now through, and again, here's where just the fun never ends, into a pyrolysis.
Burn it for waste heat and concentrate the lead in a scrubber or something?
Yeah, that's absolutely what you do. You would pyrolysize it, so you would drive off all of the organic molecules that we just saw a second ago. The heavier ones stay in, and then where do they go? Well, they go back to the technosphere, right? There's always going to be, some guy is going to want lead in his lead acid battery, and you're going to send the lead back after you've recovered the energy. So there really is no end to where these endeavors can go. Read through these for a little bit. Yeah, and this is what this is what you want to avoid. And this is the kind of the juggernaut. Like, so you do not want it back in the food chain. And they say safe disposal. Well, what's that mean? In my mind, that just means responsible recovery. Take the organics, turn them into heat. Take the lead, turn it back into a battery. So, at some point, the recycling process does become atomic. It really does. It's all the way down to the, atomic molecular level. Every one of these elements, I guarantee you, let's go back out to the dynamic periodic table. Where'd that guy go? Let's hit that again. Every single one of these elements in pure form has value. Every single last one of them is in some industrial standpoint. So if your phytoremediation strategy can recover them and then purify them and put them back, then you're making money. So, but the sticky the sticky wickets are all down here. How do you maintain it? It takes a relatively large surface area. The plants have to stay alive, et cetera, et cetera. But at the end of the day, you have concentrated them. So again, we're just going to scratch the surface on this. So other than that, I think those are the two main things I wanted to cover today. I wanted to cover the what organic materials are. We covered sugars, we covered proteins, we covered lipids. We talked about the fact that they can all turn into energy, and we also spent a lot of time talking about biosphere versus technosphere and what actually has to happen to make that happen in between, either at the large scale hand sorting like we saw last week with Eddie Stan, or some of this phytoremediation really getting down to the molecular level and letting nanoscale biology do the work for us. Okay, with that, I think we're going to head back to the bullpen for a little bit and see about getting space set up for the tub. I'm ready.